So assume that the rate of diffusion through a membrane is identical to the rate of heat transfer by conduction. Derive an expression to relate the temperature of T2 in zone 2 to the concentration in zone 1 and 2, which are C1 and C2, and the initial temperature T1 in terms of diffusion coefficient and conductivity. So I'll say that we need to relate diffusion with conduction, and we're going to assume that they are identical. That's what the problem is saying. The other thing that I said is that our conductivity in this problem here is related to heat transfer. So our K is conductivity, and our D is not diameter, but instead is the diffusion coefficient, right? Diffusivity, if you will. And I was talking about this problem here in which we have a membrane. So this middle part here is a membrane, and we have different temperatures on the left and right, and different concentrations on the left and right. And then the idea is that if this T1 is greater than T2, then we know we're going to have heat transfer from left to right. If C1 is greater than C2, we're going to have mass transfer from left to right. And that's going to be flipped if the concentration is flipped, right? So our mass flow is this, and and if my T2 is greater, then same thing happens with my Q. Right? So we don't know which one is greater than the other one. We don't really care. What we're trying to do is relate the two things as equal. And we know that the way that conduction takes place is through Fourier's law, and the way that diffusion takes place is through Fick's law. And we can write them down. So let's write them down. So Fourier's law says that Q equals, and I'll keep the negatives now. We'll talk about that. And Fick's law says the mass flow rate equals diffusion coefficient, D for concentration, dx. Right? Again, area being, right, the area, we can't really see that, but the area of this membrane here, this area here, and x being this distance here, right? The distance that the Q and M need to travel. All right. And the idea is we want them to be identical. So instead of having and there, we want to make them equal. So we want to make them like that. Right? So we want to make Q equal M. Now, why is there a negative? Well, we talked about that in the past, but the idea is that both the mass flow and the heat flow, they go against the gradient, right? They always go from high to low as opposed to from low to high. So that's why the negative is there. As long as we're putting the Q in the direction that we want, so in this case for the left, for instance, we don't need to worry about that negative. But you'll see that in this problem, it doesn't really matter if you keep them or if you don't keep them, be the same thing. Because what we're doing is we're making them the same, so we're making K A dt dx equal to d A d concentration dx. Okay, and both sides I have the negative, so they both go away. And both sides I have the area in the same area, so they both go away. And in both sides, I'm interested in the dx, so they both go away too. And this becomes a very simple conductivity dt equals diffusion coefficient, diffusivity dc. Okay, and I can integrate both these things here in respect to time, to temperature from T1 to T2, and in respect to concentration from C1 to C2. C1 being the concentration on zone 1 and C2 being concentration on zone 2. Now, K in reality, okay, is dependent on temperature, right? So theoretically, we could not take it off there, take it off the integral. But we will do on this one, just doing a little theoretical problem, approximating it there. So I'm going to go ahead and do that, and this is going to be T2 minus T1. And over here, I'm going to have diffusivity, C2 minus C1. And what I want is to have an equation that relates T2 in respect to the other things. So I need just to solve for T2. So this will be T2 equals, I'll send the K dividing, so it's going to be D over K. That multiplies the concentration gradient, so C1 minus C2 plus T1. And that is the actual relationship we were asked to draw. So it's a very simple problem. There's no practical application unless you have an ideal situation in which the mass transfer and the heat transfer are the same. It's more of a theoretical exercise for us to note the relationship between Fourier's law and Fick's law and how the analogies between the two of them. Any questions?